Welcome to this UCAN Plus Physical Acoustics Special Group webinar. Our speaker is Dr. Giulio Dolcetti of University of Trento, and the topic of discussion is characterization of dynamic rough surfaces through airborne acoustic scattering, methods, theory, and applications. And in particular, applying the methods to the monitoring of river water. Dr. Giulio Dolcetti is a mechanical engineer by training, having got his master's in mechanical engineering from University of Ferrara, did a PhD in University of Sheffield, and a stint of postdoc there, and then moved to a postdoc research position at University of Trento. And this talk is a result of his researches in the past 5-6 years on both universities. If possible, we will leave the questions to the end after the talk is finished, and then people can either raise their hand and ask questions, or put the question in the chat, and I'll try to read it. Before I hand over the microphone, as it were, to Dr. Dolcetti, just a reminder that next week, at the same time, there will be another physical acoustics webinar on use and applications of COMSOL multiphysics in acoustics. Now, if you've registered for that webinar next week, you will have had a form to fill in, which allows you to give consent for your details to be given to COMSOL to contact you. If you wish to COMSOL to contact you, then fill in the form, please. If not, then that's fine. Your details will not be communicated to COMSOL. So therefore, it's my pleasure to welcome Dr. Dolcetti and hand over the virtual microphone to him. Please go ahead.
Thank you very much, Ram, and thanks for anybody who joined this presentation. And sorry for the long title. It's quite ambitious, maybe, even the things we're going to cover. But I think this should be more like a chat about what I think is a nice, perhaps it's a bit of a niche application of physical acoustics, but it's a potentially very interesting one. There are lots of different types of wave physics involved when we look at scattering of acoustic waves from water waves, or a lot of things that could be of interest for people who have a general interest in wave physics. So, sorry, okay, now it's moving. What I will do, I thought I'd give a brief introduction, basically to explain why we have an interest in this specific kind of topic, what are the applications, and then I will touch a bit on the theory behind the method, because I think perhaps this is the right kind of audience who may enjoy this kind of discussion, and also it's useful in order to define what are the boundaries where these kind of approaches will work and where they don't. And then I'll just show some examples of reconstruction of static surfaces and dynamic surfaces, and finish with some conclusions. So the general topic that I worked with during both my postdoc and PhD was that of scattering from a rough surface of some wave. We work with acoustic waves, but most of what I will be discussing today has a more general validity even for electromagnetic waves or different types of waves. And when we say a rough surface, we actually mean a smooth perturbation of a flat plane, so more like a planar surface that has some kind of disturbance, which is smooth without discontinuities. There are plenty of applications of this kind of problem, which is the one of understanding some characteristics of this surface by looking at how it scatters waves such as sound. And applications which range from medical imaging, non-destructive evaluation, geology, communication. But perhaps when we talk about moving surfaces, dynamic surfaces, probably the most important application is in physical oceanography and in ocean science. So most of what we know today about the boundaries, the surface of the ocean, both the top surface or the waves, the interface with the atmosphere, and the bottom, so the bed and the seabed, we know it using some thanks to some scattering of some wave, which can be typically either radar or sonar. So seabed topography, wave current monitoring, weather, wind monitoring and forecasting, underwater communication detections. These are all applications of scattering of waves in some form. But there has been a bit of a separation in terms of the domain of applications. So radar mostly focused on airborne applications and mostly focused on trying to characterize the water waves, so the interface between water and the atmosphere. Radar like electromagnetic waves, like acoustic waves, have a broad range of frequencies and wavelengths. So for different range of scales, we have different types of applications. And here I'm just showing some examples which range from radar Doppler to monitor the currents, to synthetic aperture radar to reconstruct the full wave images, wave maps, and marine radar returns. So different types of applications, but quite broad and specifically, typically focused on water waves. On the other hand, acoustic applications focused mostly on sonar, on underwater applications, and specifically they looked downwards. They looked at characterizing the seabed. It's quite impressive that most of what is known nowadays about the topography of the ocean, which is 70% of the Earth cover, we know it thanks to sonar. But also the details of the geology, the kinds of sediments and the kind of structures that we see on the bed, they are typically mapped and imaged using acoustic applications. Somehow less attention has been paid using acoustics to the upper surface of the sea, so to the water waves. There are very few examples here. I'm mentioning a couple of them both from Woolsey and Dean, and they used pulses emitted and recorded underwater using some hydrophones to reconstruct the shape of incoming wave. But apart from that, there have been very little applications of acoustics to study water waves. And it sort of makes sense because radar is more efficient in air than sound. It's more difficult to generate coherent sound in air than it is in water. So it sort of makes sense that there has been this kind of shift and separation. But there are, however, some applications where the scale is much smaller than it is in the ocean, and potentially acoustics and sound can be beneficial compared to radar because they can have lower costs, they can be more flexible in the application, they can be smaller in size as well. And this is what we are interested into. And specifically, one is the characterization of the water surface of rivers. And these kind of surfaces, they show a lot of the complexity of the ocean surface, but on a smaller scale. So we see types of waves which remind of the ocean waves. We also see strong impact of the interaction with the turbulent flow. So buoys, these kind of patches which generate when turbulence is is emerging towards the surface, or vortices, scars. And quantifying and clarifying and measuring these kind of patterns is crucial. It's very important. It opens a lot of possibilities for monitoring flows without having to immerse sensors underwater, so in a cost-effective but also safer manner, especially during floods. So it opens a possibility to gather more data even during floods, which otherwise can be dangerous and difficult. It also allows potentially to detect and quantify processes which are hidden, which happen below the water surface, but have some effect, some impact on the dynamics of the surface. For instance, the presence of submerged vegetation, bed roughness, turbulence. And also, it can be key to quantify processes that happen at the water surface, but which are very easily disturbed in case we have to measure directly the shape of the surface with some intrusive method. And that includes, for instance, the exchange of gas. And that's what I'm studying at the moment, the exchange of greenhouse gases between rivers and the atmosphere, which is a very important topic with lots of implications for climate. So the way we the best way, in my opinion at least, it's one that I used quite a lot throughout my research to characterize these kind of patterns is in terms of the frequency wave number spectrum. So you surely are familiar with it, but it is basically a Fourier transform in space and in time, which allows to identify the frequencies and wave number components of a signal, of a space-time signal, such as the shape of a water surface. And the reason why this tool is so useful for this type of applications is that it allows to separate the different types of waves that appear on the river surface, such as the waves from more like turbulence generated voids and vortices. So it allows at the same time to have a quantification of the different processes going on, and also a separation that simplifies a lot the interpretation of the data. So basically, my goal for today, in the end, will go in steps, but will be to show how we can reconstruct this kind of data, this kind of information, recover this kind of information about a river surface by looking at how sound is scattered by that surface. But we'll get there in steps. So the first step is to look at how we reconstruct a static surface. So the general problem is represented here. We have a speaker, a source, which is emitting sound waves, which are scattered by a rough surface, which we do not know the shape of, at least at the beginning. And then we record the scattered sound with an array of receivers, of microphones, for example. And throughout this presentation, I will assume that our surface is acoustically rigid. This is not necessarily the case. The equations can be modified for different types of boundary conditions, but it's the approximation and it's the assumption that we use throughout most of our work. So to solve this problem, basically to invert this problem and find the solution, find the shape of the surface, we can use different types of signals. We can use optical signals, electromagnetic, elastic, or acoustic. This is a non-comprehensive list of all the papers and all the approaches that were suggested. And for each of these signals, or most of them, we can also use different approaches. So we can work in time domain, like Wolfson and Dean we're doing using pulses. We can use imaging approaches, so we can basically reconstruct spatial distribution of a function, imaging function, and then identify the surface in terms of the maxima of that function. We can use optimization approaches, machine learning approaches, or we can try to invert the boundary integral equations, and then we can do it iteratively, we can do it directly, or we can use some kind of approximation, such as Retov, Milder's, Kirchhoff, small perturbation, potential gathers as well. So of all these methods, the one that I feel a bit more qualified to talk about is the kind of approaches that we used, and it's based on the Kirchhoff approximation as small perturbation. So these are the ones that we actually discuss today. We also try and tested and touched on some other approaches. I just wanted to mention them for in case you're interested. And it's two works, basically, one by Michael David Johnson, who used a combination of random forests, so machine learning, and Kirchhoff approximation to reconstruct a parametric surface, so basically a sinusoid, which is defined by a few parameters, the wavelength, the amplitude, the phase. And he did so using only the amplitude of the acoustic scattered signal without the phase. And then there's this other work by Giulio, and he, in this case, he used a combination of multiple boundary element model coupled with an optimizer. And in that case, he did not do that assumption of acoustically rigid surface. He was investigating a more general problem with a surface with a certain shape and roughness, but also an impedance. So he was reconstructing simultaneously the shape and the impedance with this kind of approach. So if you're interested, please check these works, which I think they're very, very nice and promising in terms of what this kind of research can yield in the future as well. So, but if we go back to the Kirchhoff approximation, I just wanted to walk through the main steps that lead to the kind of methods that we use. Again, basically to highlight what are the approximations and where is the range of validity of our work. So we start as customarily with a Kirchhoff-Helmholtz equation, which says basically that the pressure at given point receiver, given by this point M here, would be the sum of some direct field and incident pressure coming from the source, plus an integral which depends on the distribution of pressure and of the pressure gradient, so the acoustic velocity, onto the boundary. And the boundary here is defined by this rho tilde, and it's a closed surface, which includes our rough surface here in black at the bottom, a hemispheric surface, and then two continuation surfaces at the sides. You may note that the sign is perhaps different to what you're more see more commonly. That's because we have a inward pointing normal vector there. So since all the sources are inside the boundary, then we know that this integral is equal to 0, where we have replaced now the incident pressure, so the pressure emitted by the source directly, which we express in terms of a Green's function. So then if we sum these two equations, 1 and 2, we end up with this function, which depends on the difference between the two pressure fields, the incident one and the actual pressure and velocity field. And then starting from the hemispheric surface, that is, it's up to us how we want to define. So we can define it with a very large radius, and then we impose a radiation condition, and then the pressure and the incident pressure will both tend to 0. Then we can neglect it, basically. On this continuation surface, that's part of the Kirchhoff approximation. We assume that the pressure will be equal to the incident pressure, and that the gradient of the pressure difference will be equal to 0. It's just part of the approximation, which is valid as long as this surface is basically far enough from our source and receiver so that it doesn't play a direct role, and also the roughness is not too large. And then we can focus just on the rough surface, and here things become a bit more interesting. So we have a rigid surface, and our equation says that we have two contributions. One is the direct field, and the other one is the integral of the pressure and velocity onto that rough surface. So a typical boundary element approach would evaluate this on a point which lies on the surface and then solve it based on that. But here we have the issue that we have two unknowns. So the pressure distribution is unknown, but also the surface shape is unknown. So to simplify this, we impose a condition on the pressure distribution. And Kirchhoff approximation says that we can assume that the pressure at each point on the surface would be equal to the pressure that we would have on an equivalent flat, rigid surface with the same, that passes through the same point with the same gradient. So in that case, for a flat, rigid surface, the pressure on the surface is equal to twice the incident pressure. So that's the approximation we do, and we just replace it inside there. And we obtain this kind of simplified equation, which is the outcome of this approximation. So effectively, in doing so, we are neglecting the multiple reflections, we are neglecting shadowing, we are neglecting all the mutual effects of different points on the surface. And this kind of approximation is said to be valid as long as the Kirchhoff condition is satisfied, where kappa is the acoustic wavelength, RC is the radius of curvature, and psi is the angle of incidence. So basically, we need a surface with a relatively large radius of curvature for this to be valid. And then Thorsos relaxed this condition. He investigated where it was actually working and find that actually, as long as this factor is larger than 0.5, we can basically assume this approximation to be valid. So we use this assumption. So once we have this equation, we choose a Green's function, typically work in 3D. We replace it, we substitute it in the equation, and we find this other equation where we have these two terms, qz and qxy, which depend basically on the acoustic wave number and on the geometry of our problem. And also we have that gradient of zeta, and zeta is basically the surface elevation at each point. Now, an issue with this relationship is that there is still a dependence on the surface shape, which is quite complex to deal with. So all the quantities in right here, they depend on the shape of the surface, which is not known. So we want to simplify this, and basically we assume we are in the far field from the surface, both the source and receivers are in the far field, and then we expand each quantity based on a point rho which lies on the flat average surface there, which means we get rid of all the tilde quantities. We have an extra exponential term here, and now we only have these two terms which depend directly on the shape of the surface, and sigma naught is now the surface over which we carry out the integration. We also typically work with directive speakers, directive sources, so we neglect the direct field and we introduce a directivity pattern function in here, which is a function that changes in space depending on the position relative to the source. And we still have these two functions that depend on zeta. And we try to simplify things even more if we can. So typically, you'll see this qx time the gradient of zeta. It depends on the geometry. It depends on the acoustic wavelength. But as long as the gradient of the surface is small, and it's small relative to the tangent of the angle of incidence, then basically we can neglect this term as well. And so we end up with this general formula, which is the one that from now on I will be referring to. We know that the pressure at any point, any receiver above the surface is the result of the integral carried out over this flat surface of the transfer function, which depends only on the geometry, times this exponential of minus I qz, again, function of the geometry, times zeta, our surface shape. So this defines our forward problem. From here, given the shape of the surface, we can calculate the acoustic pressure. But now we want to see how to invert this problem, how to do the opposite now. So now we want to, our focus is on this zeta overall. So it's the distribution of the surface, deformation of the surface height on the horizontal plane. So the simplest way to invert this would be to recast this problem into a linear problem. So for instance, as a matrix product. So we want to reformulate this in such a way that we can write an array of pressures. So where each point of the array is pressure measured at a single location, which would be the product of a transfer matrix that depends on the geometry mainly, probably something related to this H function here, and then an unknown Z array, which is directly related to the surface elevation, which allows us to calculate surface elevation directly. If we can write this equation in this form, then we can just invert this transfer matrix and estimate Z, which is what we want to do. The issue is that in QZ, we have that dependence on the geometry, on the position of the receivers in M, and this makes it more difficult to separate these two terms. So we try to find approaches that allow us to linearize this problem. One approach is we called it the short array approach. It was introduced by Krinkin et al. 2016. And basically it just averages the QZ over the receivers, or it picks one single value of QZ for each receiver, which is representative of all of them, which is why it's called a short array. It's valid as long as the position of the receivers does not change too much. With this approximation, we get rid of the dependence on M, which means if we reconstruct the distribution of this exponential, we can just calculate the logarithm, we know QZ, and we can estimate zeta. A second approach is directly derived from the first one. So we still have that same averaging of QZ, but now we also subtract B naught. So we subtract the pressure, which is reflected by the flat surface, by the flat average surface, and that is independent of zeta. It leads to this -1 term here. It's basically the same, but the advantage is that now if zeta is a small function, so when QZ zeta is a small function, then P minus P naught will also be small, and that helps with the conditioning of the problem and with insurgence of biases. I will show that later on with the regularization especially. The third approach is small perturbation. So in this case, we simply assume that QZ zeta is much smaller than 1. So we work with either small surface deformations or with a relatively low frequency. And then we just expand it, and everything in orange and brown here will become part of this transfer matrix, depends only on the geometry, and then we have directly here zeta. So with any of these three approaches, we can find formulations such as a matrix product, like the ones at the bottom, and then invert the problem. Will be very straightforward, but typically the number of receivers that we have, and M, is relatively small. It's typically smaller than the number of points where we want to reconstruct the actual surface shape. So this is a rectangular matrix, sorry, that has more columns than rows, so it's an underdetermined problem. And then to solve it, we draw from some work in near-field acoustic holography. We do a singular value decomposition, a Kirchhoff regularization. I won't go into too much detail, just to refer you to these papers if you're interested. Right, so I'll just show some examples now. This was the first experimental validation we did, and this was using a 3D printed surface. You can see the scale here. It was about 20 centimeter length. The amplitude of the waves was 2 millimeters, so the standard deviation was 1 millimeter. It had a random shape. It was generated starting from a power function spectrum. We used only the short array approach in this time, and we had a single microphone which we scanned along this arch, took 15 to 60 measurements, and then combined them to reconstruct the shape of the surface. Here we work with a harmonic signal at single frequency, 43 kilohertz, and you can see here the example of reconstruction. So The solid line is the actual surface, and then the dashed lines are reconstructions with different numbers of microphones. Then in a following work, we expanded. Starting from that, we wanted to go into a bit more detail. We tested this time the three approaches. We compared them. We used a line array of microphones. This time it was 34 microphones taking measurements at the same time. And here we used a white noise signal. In this way, through a Fourier transform of our scattered signal, we could recover the signal at different frequencies at the same time. And then for each of these frequencies, carry out an inversion that would make things a lot more efficient in terms of taking the measurements. And we did both numerical simulations and experiments in this case. So here you can see some examples of the reconstruction. So the black line again is the actual surface shape, and then blue lines are the reconstructions. We introduced these three metrics. So one is the deviation SC. It's basically the RMS difference between these two lines. You can see it here normalized against the acoustic wavelength and plotted against the surface height, surface amplitude, again normalized by the acoustic wavelength. So basically, on the right-hand side here, we have a higher surface elevation or a higher frequency of sound. On the left-hand side, we have smaller surface deformation or a lower frequency. And you can see, as we would expect, that the small perturbation method behaves worse than the other approaches, especially when the surface amplitude increases. That's exactly what we would expect. Then we looked at the bias, so the average of the error, and we found that the SA, the short array approach without preconditioning, was biased, especially for small surface perturbation or for low frequencies, but the bias was eliminated by that preconditioning approach. And then we looked at the probability of failure. So as you can see in the example on the left here, there were cases where the reconstruction was failing completely. That was due most likely to problems with unwrapping of the phase. And the probability of failure, we found it to increase a lot when either the surface was becoming higher in amplitude or the frequency was increasing. So we found that basically if we worked with higher frequency, then we had more accurate results, but potentially less robust. And on the other hand, at low frequencies, we had less accurate results, but more robust. So finding the perfect recipe for reconstruction would require some sort of balance, which somehow is expected, is what we would expect. But we also wanted to see if we can do something different. And here I'm showing this for the small perturbation approach. We can actually do something very similar for all of the other approaches. I'm highlighting here the dependence on the frequency of our signal, which is kappa 1 in this case. It's a certain frequency. As you can see, the acoustic pressure depends on the frequency, of course. Our transfer matrix also depends on the frequency, but the shape of the surface, of course, that doesn't. So this is our typical underdetermined system that we had previously. So we have our array of pressures, our transfer matrix, and the array of surface elevations. Basically, we can write the same equation and the same system using different frequencies of our signal, and we can append them at the bottom of each other. Basically, we can build a bigger system without changing the array of the unknown surface. So we can basically transform what used to be an underdetermined problem potentially in a overdetermined problem. And also we can potentially combine the advantages of different frequencies, so have more accurate approach, but also robust. And in this case, of course, it's a overdetermined system, so we can use some least square approaches, for instance, without having to do the decomposition, singular value decomposition. Here I'm showing some results. So here the reconstruction using multiple frequencies at the same time are the red lines. You can see already how the fit with the original surface is improved. And also we have more robustness, but also here at the top, I'm showing the RMS error normalized by the wavelength relative to the amplitude again of the surface elevation. And here the multiple frequency reconstructions are the red squares, whereas all the dots are results of the simulation or the actual measurements with a single frequency. And as you can see, we have an improvement both in the accuracy, but also crucially in the robustness. So we don't see all these failures that we used to see there. So this seemed to be like an ideal approach, in our opinion, to reconstruct this kind of static surfaces. But of course, these are static. And so if we want to translate that into moving surfaces, we have to take into account that because the surface is moving, then there is a Doppler shift, which changes the spectrum of our signal and potentially makes it a lot more complicated to detect what happens at multiple frequencies. So let's see instead what approach we used for a dynamic surface reconstruction, which is an emanation of the same approach I showed just earlier. So here I've taken again the small perturbation approach equation. We actually derive this only for the small perturbation approach. And here I have highlighted what terms of that equation depend on time. And it's basically just the surface shape, if it's moving, and the scattered pressure. This is the pressure reflected by the flat surface, which is it's not moving, and this depends on the geometry, so also it's not moving. So essentially, we can build the same kind of matrix representation as before, where now we have, instead of having an array of pressures, we have a matrix where each column is the pressure distribution at a different time step. And the same we can do for the surface elevation. And now we can introduce a Fourier transform operator, which has its inverse. So the product with its inverse Fourier transform is equal to the identity matrix. And basically we calculate the Fourier transform in time of our pressure, which gives us basically the Doppler spectrum. And on the right-hand side here, we have instead the Fourier transform of the surface. So we have the surface spectrum. So you can see how both are directly related by the same transfer matrix or transfer function that we had earlier. And we can do one more step. So we can also introduce a Fourier transform in space. And again, because we have both its inverse, so we can basically insert it in between our transfer matrix and the surface spectrum. And we end up with something like this. So we have the Doppler spectrum, which is equal to the product of a different transfer matrix now, but still it's easy to calculate and depends on the geometry, which multiplies the surface frequency wave number spectrum, which is basically the transform in space and time of Z. So here I've written it again. So this is what this is one example of Doppler spectrum. For instance, you can see how broad the spectrum becomes due to the movement of the surface. So we have basically a compilation of many of these, each one calculated at a different receiver location. And then here we have the unknown surface frequency wave number spectrum, which is the same one that I was showing earlier was our goal for today. It's just has been rotated. So once we have this kind of formulation, you may already expect what is coming next. We follow the same exact approach. So we can write it as a linear process. We just invert this transfer matrix. Again, we will have that issue of having less receiver locations that points on the than in this case combinations of frequency and wave number. But again, we can use the same kind of approaches and invert this process. I'll show some examples. So we validated this in the lab. We've done some tests initially in a wave flume at the Laboratory of Verification and Validation at the University of Sheffield. We had a wave maker, so that's a paddle that is going up and down. It's controlled by a CNC motor there, CNC controlled motor. We have an array of 30 microphones along a line. So, and we had different types of surface deformations. We had sinusoidal waves, but also more random general pattern of 2D waves in this case. And we worked with a single frequency because of that Doppler broadening of the spectrum. And these are some of the results. So on the left, you see the Doppler spectra recorded for a sinusoidal surface, and for a random surface, you can see how different they look. This is more like, again, almost like a harmonic dependence also in the Doppler spectra, whereas this is more like a broad spectrum. And then applying our method to these spectra, this are the reconstructions of the surface frequency wave number spectra. So the contours indicate the reconstruction, the outcome, and the crosses there and the dashed line indicate the expected, the expectation from the theory. So a pretty good fit in both cases. And then we wanted to test it on actual surface deformations in rivers. So we've done some tests initially in the hydraulic lab at the University of Sheffield, where we have a model of an open channel flow of a river. And then we did also some tests in an actual river Loxley in Sheffield. In this case, the patterns are three-dimensional, so we needed like a 3D distribution of receivers, and we used a sound camera produced by Siemens that has 49 MEMS microphones, or 81 in this extended configuration. And here, these are the results. So in this case, we have a 3D representation. So we have a three-dimensional frequency wave number spectrum with both components of wave number. So we actually reconstructing the full 3D array of the spectrum. So here I'm showing the cross-section through the streamwise direction, the direction of the flow. And at the bottom is the cross-section through the lateral direction. And again, so left-hand side is laboratory, right-hand side is field, and the contours are the measurements and dashed lines are the expectations. So again, pretty good fit, but also crucially, the ability of this method to identify the different types of waves there. So from here, we can do lots of things potentially. We actually reconstruct not the amplitude of the spectrum, but the imaginary spectrum. So we can also invert the spectrum in order to reconstruct the shape of the surface if we wanted. We can look at the frequency spectra. So this is the comparison between the directly measured dashed line and the reconstructed surface frequency spectra. We can fit those spectra in order to quantify the depth, the velocity of the flow. So here I'm showing the error in the estimated flow velocity was below 9% and 13% for the laboratory and field, respectively, which was not too bad for the first initial test. So potentially that allows to do a proper full characterization of the surface in a very efficient way, without contact, and in a way that can potentially be applied flexibly and whenever it's needed. So future developments will probably see, I think there are plans already for further field validation on a wider range of conditions and scales. It will be nice, and probably at some point we will look into introducing still some multiple frequency application, perhaps separating the range of frequencies to avoid the crosstalk with Doppler. There are the applications of machine learning and Bayesian approaches that Michael David Johnson was working on. They look very promising in terms of static surfaces. So of course, it would be great to see if those can be extended to this kind of approaches as well, especially Bayesian approaches, as they give an estimate of the uncertainties as well. And ultimately, the goal will be to have something that can be operational and potentially that can be built onto UAVs or drones and deployed during floods or wherever it's needed in order to obtain the kind of information where it's needed, when it's needed, which can be fundamentally this kind of cases when time is really, really important. So this is the end. I'll show this, which is the full list of the references in case somebody wants to take a snapshot, or presumably that will be on YouTube later on. And these are the beautiful people that I've been working with these topics. So I wanted to thank them and also thank you very much for attending this. And, please, I hope there are some questions. Thank you.
Well, thank you very much, Giulio. That was very interesting talk. I will open the open the floor for questions. Apologies. You can ask questions in the Q&A or raise your hand and I will let you speak. I'm sure there will be questions. Any questions? Right. Okay, one question is from Spirus. At what distance can the microphones be placed?
It depends on the frequency. It depends on the scale of what we want to measure and what we want to achieve. It's a very interesting question, to be honest. We work with different distances in the lab and in the field. I think in the field we have a distance of about 50 centimeters, 60 centimeters, something like that. But we did some numerical tests, and as long as we don't have issues with the wind or with anything affecting the propagation of the signals, we could extend it to a few meters fairly easily. The limitations stem in the dimensions of the array, which of course the farther we are, the bigger the area which is imaged. And then we need an array that somehow is able to cover it. So I think I didn't quite have a time chance and probably wasn't the right occasion to discuss it, but there is a strong effect of Bragg scattering, which sort of identifies the scales that can be reconstructed, and that is spatially dependent. So effectively, we are filtering the surface with different scales in different locations of our surface. So that, especially if the surface is not homogeneous, it's something that has to be considered as well in scaling and increasing the distance. So in that sense, it really depends. It's one of the things that need to be designed properly. And I think now we have a sort of good understanding of how this system works so that we can design it properly. In terms of how close it can go, then it depends mostly on the approximations that I showed, and that's the reason why I was highlighting them. So at some point, we will not be able to neglect the shadowing or the effects that come from the not being so much in the far field anymore, or multiple reflections.
Thank you. Ariana asks, how do you see the application of your method to aerated flows?
Another very good question. So irradiated flows, they're basically flows with lots of bubbles and with lots of foam, let's say, or with lots of discontinuities in water. Our method, since it's based on the Kirchhoff approximation, and as I showed it requires that the surface is continuous, but most importantly, there is a limitation on the radius of curvature, and we neglect lots of things that actually probably wouldn't be satisfied in those kind of flows. There are potentially, I think, some applications as we worked with Doppler, and so that even the last method is based on Doppler. And in that, perhaps it's possible to relax the condition on the surface, considering it as a more general scattering from obstacles, which could also be water drops, for instance. And then potentially it's possible to do something in terms of looking at the speed of these scatterers and obtain also some spatial information, which at the moment I think typical Doppler applications don't have. So it's very interesting applications. I don't have an answer now, but I hope that somebody will look into it in the future.
Thank you. If there are no more questions, I have a couple of questions. One is a short one that you're using ultrasonic frequencies for your measurements. How applicable are they outdoors? Because obviously, if you're using, I don't know, 20 kilohertz, they don't travel very far in air. So you need to be pretty close to your river. How feasible is that in outdoors?
It doesn't have to be ultrasound. In fact, it all depends again on the scale. So imagine that basically the kind of surface waves and scales that we can see, the shortest, so there is sort of a diffraction limit. So the shortest wavelength that we can recover is about half of the acoustic wavelength. So we
Just because talking in terms of physics, the frequencies you work with and your assumptions are in the scattering domain. You assume sound is scattered, but if we move frequencies to lower frequencies and larger wavelengths, where the wavelengths are larger than your roughness size, whatever that is, we get into a different domain and different physics, where the surface behaves like a not a rigid surface, but an impedance surface. And there you can determine roughness parameters by reflection of the sound from that surface. There's a lot of work I've been done, and for example, by Keith Attenborough, who was here but left, or myself, and we used again a form of BEM, which was developed by Simon Chandler Wilde a long time ago, and perhaps adopted by ourselves to look at that, and you can do that. So, have you considered low frequencies and different domains? You know, moving from scattering domain.
Thank you. I mean, it's of course I am aware of those works. It would be very interesting, I think, to see if the two can be combined. There are again, it's a complex topic. So one issue we will have to face if we work with low frequency, like audible sound or low frequency audible sound, especially, is the kind of impact that can have, especially if we aim to apply it on an actual river. perhaps going on the whole day, that could be an issue. We so far we started from Doppler. That was our starting point, and of course we wanted to work with high frequencies because we wanted to look at scattering, and we wanted to see a Doppler shift that was representative of the surface elevation. And then we built up from there, and potentially you're right, it could be the right time now that we start to see what happens in the lower spectrum of frequencies, and perhaps see if we can merge different approaches and gain even more understanding.
You're right. I see problems with using audio frequency, both in terms of annoyance and also the background noise, which needs to be encountered. So ultrasonics in outdoor conditions has advantages because you don't have that much, hopefully, that much background noise, and as a consider annoyance doesn't have to be taken into account. But there is a limit to distance. Anton.
Just to add to Julio's comments, to your answer, to your question, sorry. I think low frequency, small perturbation method Giulio is using in his model should be able to account for low frequency effects. So as far as I understand, Giulio, that should be a working model.
Well, yeah, but what Shram was saying, I think, is that I mean the physics change, and we've only seen things from the perspective of scattering, whereas and we assume that it's a rigid surface. So perhaps when we move to lower frequency, we will have to consider other things as well, which were not part of what we've looked at so far, because it was just not the application that we were using.
If the rigid surface is effectively modeled with impedance, then your approach with small perturbation should be able to act in relatively accurately then. So, but obviously if there are some other losses involved, physics involved, then yeah.
Yes, another point which probably you have considered is that you're measuring effectively surface roughness. I assume you can link the surface roughness or surface shape of the surface to other parameters in the river, for example, its depth or perhaps its turbulence. I'm sure you have considered them, but are they being investigated?
It's an ongoing work, and it has been the other half of my work until now. There's still a lot to be done with that respect, because it's difficult to detect and quantify the interactions and what really is responsible for the surface deformations. And one of the reasons is that it's very difficult to measure the surface roughness. So we're using sound, but if we were trying to find an alternative approach, it would be very hard. So in the laboratory, we use images, we use cameras, but we have to add some dye to the water in order to make it opaque. Otherwise, we just see through it. So it's two researches which go hand in hand, and they go along together, and really need each other, support each other in a way. So the more we can measure the surface, the more we can identify and understand how it responds to the flow. So with those frequency wave number spectra now, we can understand a few things. We can estimate the water depth. We can estimate the flow velocity. We still haven't got to clarifying the details of turbulence, for instance, or of other aspects. But I think that will come at some point if we develop robust ways of measuring.
Great, thank you very much. And I think since we're past 2 o'clock, we don't see any new questions. That leaves me to thank Dr. Giulio Dolcetti for his very interesting talk, and our participants and attendees for joining us. And hopefully you'll see you next week in the COBSOL webinar. See you all.